Hello, hi, welcome to JuliaCon 2022 workshop on the introduction of graph computing. We're excited to join you here on this exciting topic. My name is Yadong Li. I'm the CTO and the co-founder of Julius Technologies. In the past 15 years, also I have been spending a lot of time building the most complex models and analytical systems for big banks, having accumulated a lot of experience on how to build these enterprise complex systems. So today we're going to cover why graph computing is such a great solution for enterprise computing. And we're going to use a lot of concrete examples to illustrate the key concept and benefits. So here I'm going to share my screen. Yeah, if you can see the screen, if you can type in the chat room, let me know it's visible. Okay. So today's workshop, this is the agenda for today's workshop. First, I'm going to make a short presentation covering the basic concepts and the key benefits of graph computing and why it's important. Then we're going to go through a benchmark study showing some of the common platforms available to Julia and Python developers, and do a benchmark study of these different platforms. Then we're going to use some of the real-world examples to illustrate how to build complicated, large-scale, and realistic graph computing solution using Julia's platform. So at this part of the presentation, my colleagues from Julius Technology will be joining me. So first, what is graph computing? Graph computing actually is a part of this broader field called graph technologies. Graph technology has recently been trending, attracted a lot of attentions. Gartner forecasts that 80% of data and analytics innovations will be made using graph technologies by 2025, up from 10% from 2021. So this is a huge forecast of growth and a huge vote of confidence by Gartner. So there are several different categories of graph technologies. So for example, people are most familiar with our graph databases and such as knowledge graphs. So for example, if you look at the social network, the data can be organized as a complicated graph. So the second category is graph analytics or graph ML. So this is really about how to write algorithm to analyze the graph. For example, find the shortest path, try to find ways to dissect the graph, and also try to see if graphs are connected, nodes are connected to each other. However, these are not the key, the focus of today's workshop. Today's workshop is about the graph computing, which is about how to build systems and applications as graphs. So the platform that in this space include Dask, Airflow, PyTorch, TensorFlow, Dagger.jl, and of course Julius. So these software provide ways to build complicated systems and applications as a graph. So first question you may ask is, why do we want to do that? Why do we want to build a system as a graph? So this goes back to the point we mentioned earlier about enterprise building enterprise systems, in particular enterprise data and analytics. So for people who have worked on enterprise software, you can appreciate that the enterprise software is a totally different animal from your desktop application or mobile application or even web application, because they tend to be like complex, very opaque, heavy, and also these systems tend to run for a long time. Many of them run for decades. They accumulate tons of technical debt and entropy over time. They tend to become overly complicated, bloated, difficult to support, require an army of developers to maintain and keep it up to date. So if you look at why the enterprise system is so difficult, so expensive. Of course, a part of the reason is the organization itself, like that certainly bring a lot of complexity to the systems. But if you focus on the technology side, I summarize these 6 different challenges purely from technology point of view. We call it scalability. We have acronym for them called STELLAR. They particularly named. They particularly are scalability, transparency, explainability, lineage, adaptability, and reproducibility. So of course, these 6 are not an exhaustive list. There are many more challenges, but we think these 6 are really the key difficult challenges to solve in enterprise computing world. And if you look at these 6 different challenges, to solve one of them is not easy. To solve all 6 of them together is a very tall order. So the reason why a current enterprise system becomes so bloated and difficult, complex, a big part of that is the current development environment or platform doesn't supply general solution to the Stellar challenge. So therefore, it leaves the task to individual companies to have to build these solutions on their own. So these ad hoc solutions tend to be inadequate, like probably not consistent, and also not optimal. So as a result, the system becomes more and more complex when you add more and more of these requirements and features. So how graph computing can help? So this slide shows a very high-level summary of the key difference between the traditional programming paradigm and the graph computing paradigm. So in the traditional programming paradigm, we write a lot of code as functions. Basically, if you look at any programming language, it eventually come down to a collection of functions. These functions can be compiled into binary code, then they will be executed by a runtime. So the runtime can be a single process or multiple process running on cloud. It doesn't matter. The key point here that the runtime, after executing your code, give you the results magically. Hopefully, it's correct results. But however, the runtime tend to be a big black box. It doesn't give you any insight on how the results were produced. It doesn't give you the intermediate results. It doesn't give you visibility to any of these like input-output throughout the entire logic. So if you want to track or log some of these intermediate results, the programmer has to make an effort either to log it somewhere, a file database, or attach a debugger to see the intermediate results. It's very difficult to understand the system and also make changes. So in comparison, graph computing works in a different way. So it starts with some kind of graph programming format or syntax. So for example, some graph programming solution use drag and drop GUI to create these graphs. Most of them follow a certain API to create graphs. So once we have the graph programming that defines the logic, we don't execute the code directly. Instead, we create an intermediate representation called the computation DAG, which is a directed acyclic graph. So this DAG basically captures all the logic flow of your application or a system. Then this computational DAG will be executed to give you the final results. So the key difference is that we have this intermediate representation called computational DAG. This is tremendously useful, and it actually later on in the next few pages, we're going to show how to solve the stellar challenges we listed in the beginning. So in this slide is a quick explanation of what DAG is, computational DAG is. So we have a piece of regular code, and on the right-hand side, we have the corresponding DAG representation. So the computational DAG is basically a graph with directed edges, but without any circles. So basically, any program or systems logic reduced to a DAG representation. So the DAG is a very generic representation, regardless of how complex or simple your computation or system is. It already conceptually reduced to a DAG representation. So for example, if you look at a simple Excel formula on a few Excel formula connected on a spreadsheet, that is nothing but a DAG. Also, when you see these complicated IT system diagram, you notice these complicated arrows and boxes, that is nothing but a DAG as well. So therefore, like regardless of complexity, they all reduce to a DAG. Another point is also extremely important, that it's acyclic. So when the DAG is acyclic, it guarantees that when we execute this DAG, every node is only hit once, because there can be no circles. So therefore, this is a very useful property compared to the traditional programming language in functions, which is are permeated with loops, if conditions, that make it much easier to infer its runtime behavior. Because when you have a loop, you may looping over a variable that that determines your number of iteration. So just before the execution of function, you have no way of knowing how many iterations that loop will iterate over. But with the DAG, if you iterate n number of loops, it will create like n subgraphs. From the graph topology, you can easily see and estimate the computational resource and the cost of that computation, make it much easier for the machine to optimize and analyze and distribute automatically. So this is really the key benefit of having a computational graph. So this page really answers the previous question, like why graph is such a great solution and generic solution to the stellar challenges we mentioned earlier. So first, the DAG is a generic representation. Any computation is reduced to DAG. Secondly, we already mentioned that for example, the DAG is great for distribution scalability, because you just need to write one distribution algorithm that works on any DAG, then you have solved all the distribution problem for all the system that can be mapped to a DAG, which pretty much covers everything. And also the other challenges, transparency, explainability, and lineage, all of them come for free within a DAG, because the DAG has the full information about how the data flow from one node to another, how the computation logic works on individual nodes, and how the final results is computed. So the last, adaptability and reproducibility, these are a bit more challenging than the previous challenges, because for example, first, let me explain what they mean. So for adaptability means that when you have a complex system, it should be easy to make changes. So it shouldn't take a lot of effort, write a lot of code to make changes to your systems. Reproducibility means that you should be easily create copies of your system, and to use those copies to do experimentation and run different scenarios. So in practice, it sounds easy, but in the enterprise setting, it's incredibly hard, because for a complex organization, oftentimes they have one gigantic production system that is so complex, costly, already too expensive to support. To make identical copies of that system most of the time is out of the question for most organizations. And to make changes for a complex system, actually, you need to touch many components of the system, potentially running on thousands of computers. It's a very difficult job to coordinate and plan that change. Oftentimes, even simple changes can take months or years to implement. So just having a graph solution is not going to be adequate to solve the adaptability and reproducibility problem. So what we need here is really a low-code way to define your graph logic. So if we have a way to create a graph solution that is also low-code, then we can easily take this low-code representation of your production system and recreate it anywhere. Or we can take this low-code representation, make modification to this using this low-code representation, and regenerate the system with the new functions and features. So therefore, the key point here is that in order for the graph solution to really completely solve for the stellar challenge, we need to make it low-code. So we have to add a L to the acronym to complete the stellar word. One of the L is for lineage, another is for low-code. So this is really the key message you want to share in the first part of the presentation. So this slide highlights what Julius technology does. So I promise this is the only slide with a bit of information about us. So Julius offer a auto-scaling low-code visual graph computing solution for building transparent and adaptable data and analytical pipelines. So Julius is a generic stellar platform for building enterprise systems. It allows enterprise to build a stellar system at a fraction of time and cost. So I see in the comment there are some comments about the examples. So we're going to have plenty of examples in the rest of the workshop. You'll see how it works in practice. So basically, here what we provide is a generic development platform that already have the stellar challenges solved, so allow developer to focus their energy building the business use case. And for Julia developers, this means that we provide great tools for Julia developers to tackle complex enterprise problems, where we see Julia can have a tremendous opportunity and the need in that space. So now let's move on to explain a bit better on this low-code graph programming point. So of course, graph computing starts with some kind of graph programming method. So how you do your graph program actually have tremendous importance in the performance and the characteristic of your graph computing solution. So for example, here we can quickly say that any GUI-based solution, drag and drop solution, is not going to scale because you cannot drag and drop thousands of nodes and create a graph from that. So it has to be some kind of programming approach for the graph solution, graph computing solution to work for enterprise settings. So in this case, here we are showing like how the typical way of creating graphs, like a typical graph programming approach, and also the Julius low-code declarative programming approach. So in the conventional approach, how we create graph, for example, this is the approach that followed by like a TensorFlow, like Airflow, all of the typical current graph computing platform is you write in traditional programming languages, most likely Python, with some special API, most likely Python decorators. And once Python code is executed with this special API, instead of computing the numbers, it actually records the logic of that computation in the graph, do a lot of housekeeping and keep track of the information in the graph so that it can be executed later on as a DAG. So this is a typical recording approach. So the Julius low-code like graph programming approach actually is based on a DSL, domain-specific language called root DSL. It's a very simple declarative syntax, only with minimum features. It is specially designed for graph creation. So because when you do the standard recording approach, you have to like run the entire program from beginning to end to generate the graph. In comparison, when we generate a graph from root DSL, that happens directly. It doesn't have any intermediate. We don't have to run the program from beginning to end to create a graph. So therefore, the graph creation using root DSL is orders of magnitude faster and much more memory efficient. So let's like probably dig into a bit more detail in this point, which is the important point I want to explain clearly. So when you write graph logic in the conventional programming language using like the typical recording approach, you basically writing with the full general purpose programming language features such as like types, classes, functions, loops, and branches, polymorphism. All of that are at your disposal. So this is a very complex set of language features. But if you look at the final output you want to produce, it's a computational DAG which doesn't have any of these features. It doesn't have loops. It doesn't have branches. It doesn't have polymorphism. It's just a computational DAG which pretty much like with all of this information removed. So if you look at the traditional approach, so in this case, you write a lot of code, and then just make a lot of effort to write the graph logic using the traditional programming languages, then only have to have them like undone, the effect undone removed in order to create a computational graph, because you have to run the entire program to record them. And also you have to unroll the loops, like you have to resolve the branches. You have to remove the map out the polymorphism. So this seems to be a lot more wasted effort. So the reason you're doing like unnecessary work on each of these steps. So the reason that you're not creating the graph using the right tools. You are using something that is not designed for graph creation. So in comparison, using the root DSL, we have a low-code syntax that directly map to the graph topology. It just defines nodes and dependencies. It doesn't support many of the complex language features like functions, loops, if statement, whatever. But it does support polymorphism, because that is, we do want to build different pipes according to the different data types. That dynamic behavior is important. So therefore, it's much simpler set of features in the root DSL, and it make it much easier to create a graph, because pretty much this root DSL can be directly mapped and expanded to graph without much additional process. Compared to the recording, you have to do a lot of work to unravel your traditional programming language into graphs. So this is also I want to make another point, which is if you look at the Stellar challenge, we want to solve this Stellar challenge end to end. So once you have the computational graph, some of these Stellar challenges can be solved. For example, distribution can be automatic. But if you look at end to end, this part, this part cannot scale and cannot be easily distributed, you haven't solved the Stellar problem end to end yet. So this is one of the issues with the traditional graph programming approach. For example, if you create a very large graph that can have hundreds of millions of nodes, when the graph becomes very large, the bookkeeping information also grows. The recording that graph can be much more expensive than like executing that graph for very large graphs. So in this case, for the graph to scale to the enterprise level, you have to solve the parallelization and also the same Stellar challenge for this graph creation part. So this is another point I want to make. So therefore, rely upon the traditional recording approach actually only solve half of the problem. Like this part still remain challenging, like unresolved. In comparison, go with the root DSL, we solve the entire end-to-end, like from the graph creation to the graph distribution and execution. So now let's quickly back up the claim by sharing some of the benchmark studies. So here, this is a comparison between Julius graph engine and a few very widely available graph computing solutions. We did a benchmark that using a simple example, which I'm going to show a bit more detail later. But here the point is that when the graph size increase, many of these alternative graph computing platform cannot handle the large graphs. So none of them actually managed to finish the execution of 500,000 graph within reasonable amount of time. I waited 6 hours, couldn't finish, I have to stop. But for Julius, its orders of magnitude faster in terms of graph creation and execution, only take 15 seconds. So that's actually not a typo. 15 seconds to create and execute the graph of size 500,000, which is many orders of magnitude faster than the rest of the comparison alternative platforms. So at this point, you may think that yes, it sounds interesting, but does it mean that in order to use your graph computing solution, I have to code everything I have using your root DSL? That is typically not the option at all, because you may have complete library that already have been battle tested for years. It's just too valuable to throw that investment away. So I think the key point here is that you don't have to recode everything you have using the root DSL. So what we provide is a atom, very simple atom interface. We're going to show later on in the examples that give the very simple interface to interact and interop with the traditional program languages. So for example, when you have Julia, C, C++, Python, .NET, Java, like the typical mainstream programming language, you can pretty much like plug in your libraries into this atom interface. So difference between the root DSL and atom is that the root DSL governs the creation of the entire graph pipeline. But in terms of what's happening at individual node, that is determined by the individual atom. So basically every rule in the root DSL refer to atom that basically specify what logic to apply in individual nodes. So in this case, the atom is named obviously after atomic, meaning that it only affects one particular node. It doesn't affect any other node in the graph. So once we have these two construct defined, then Julius graph engine will take them and automatically generate your entire system according to the logic graph programming in root DSL and also the atom functions or atom objective defined interfacing with traditional programming function style of programming. So this is this actually makes the entire system building like a much easier because the system is created, the entire pipeline is created for you. You don't have to write a lot of imperative code to create the system. So I think this is a quick conclusion of this part of the presentation. So the low-code graph programming, if you take away one point, this point is really a critical ingredient for graph computing to realize its full potential. By adding this low-code feature into graph programming, we actually offers a generic solution to the stellar challenge in building enterprise systems. So at this point, I'm going to quickly walk through a bit more detail of this benchmark. And then later on, we're going to go through some detailed tutorials to show the root DSL syntax and the atom interface. So this benchmark study actually is quite straightforward. So basically, use a very simple Fibonacci sequence type of calculation, and also we computed the summation of all the even terms of the Fibonacci sequence. So in this case, to make it more interesting, instead of running on scalar, we run on them on a vector of length 10. So as you can see, when you increase the terms here, you get like a y, which is a very narrow but a deep graph. But as the summation of the even terms is a very like both deep and wide DAG. So of course the deep and wide DAG is more challenging to execute, to orchestrate. So then we use different graph computing solution to solve these two identical problems, and look at their timing. So the timing we already reported. It's a dramatic improvement to have the root DSL. So here we're just going to quickly look at the code. So this is a Dask implementation. So basically Dask, as you can see, uses decorators. So to decorate the Python function. So with these decorators, when the Dask runs, it doesn't create the results right away. Instead of it added information to the graph data structure and all the housekeeping information so that it can be run in a distributed manner later on. So very similar, Dagger JL has a very similar approach. Like we have this spawn macro that specifies the task will be recorded on the graph and run later on. And also the TensorFlow implementation is similar, but it has a decorator like this. So the last, we're going to cover the Julius implementation in more detail in our first example. But before we do that, let's just quickly show how to sign up for the Julius free developer website. So basically, all the examples we're showing today are available through our free developer website, and you can like anyone with a Google email can log in and get access to our webpage for free, and have you can play with our tutorial examples we're showing today at your leisure. So here we just need to click this sign up link. So I'm going to share this. Yeah, you just click through, and you can go to go to our web environment. So here you can see that we have the entire example available. So we're going to go through, next we're going to go through this quick start example as a first tutorial of the graph computing. But let me also share the Julius graph, this sign up link as a banner. Yeah, I shared the sign up link in the chat. So now maybe it's a good time to see if you have any questions. Like let's probably take a pause and look if we have some questions. So to ask questions, please use the Pigeonhole link, which should already be on the links. So
Yadong, for some reason we only see the GitHub page. We couldn't see while you were logging into Julius web server.
Oh, sorry. Like so what do you see?
Just the GitHub page. We can't see the Julius graph server.
Oh, okay, okay. So do you see it now?
Yeah, it's like we see just the only GitHub page. Maybe you can stop sharing and start sharing again.
Okay. So let me try that.
Yeah.
Okay. Yeah, that's great. So okay, right. So I think now let's probably see if we have any questions from the audience. To ask questions, please use the Pigeonhole link. Okay, I see some questions already being answered. Yeah, there's a question about how a relatively small research project benefits from graph computing, or is it an overkill? So it's harder to say in general, but I think it's true that the bigger systems and bigger applications will benefit more from the graph computing. The smaller project tend to benefit less, but if you're oftentimes the smaller project have a potential to grow in complexity. So at some point you may want to revisit that decision. Okay, so I think we have the questions answered. So let's go through the first example, which I'm going to walk through the key syntax of the Julius root DSL and the Atom interface to interface with the traditional programming language. So just one quick point to make is the Atom is also a great way to control the granularity of your node your graph, because you can have an atom that does heavy processing, a heavy atom. That means your graph will have fewer nodes for the same task. Or you can have atom that is very granular, does a little bit of work. Then your graph will have a lot more nodes. You have full control of switching the logic between the number of nodes, trade them off between number of nodes and what did happen in each individual node. So here, in this tutorial, we're just going to highlight the key syntax for Julius, RuDSL and Atom, and show how easy it is to implement the Fibonacci sequence we shared earlier in the benchmark. So the Julius Atom is a very simple abstract struct defined in Julia. So here is a very simple atom that is defined to compute the weighted sum of arbitrary number of data frames. This will be used to compute the Fibonacci sequence on data frames. So the atom is a abstract interface. Here we're using a substruct from the base atom. It's called datum. So this is the most generic and commonly used atom type. It can capture any kind of data processing or numerical computation. There are different types of atoms that you can define. So for example, some atom interfaces are specialized for adjoint algorithmic differentiation, AED implementation, but that is not the topic of this part of the workshop. So if you're interested, you can get access to the web environment and also look at the AED example. You get all the detail there. So in this case, you can see that the atom just have a very simple interface, a single function called for data. Take the in this case datum object as the first argument, then take a arbitrary number of data frames, then just internally does a weighted sum and return a vector. So we choose to define all the atom to return vectors to be explicit that any atom can return multiple objects. So if you want to return a multiple object in one shot, it's very easy to do following this interface. So here this is just plain vanilla Julia code, nothing special. And from that, you can easily see it does what it's supposed to do. When you have a few data frames, you can compute the weighted sum of them. Also, besides this vanilla, like plain vanilla Julia way of declaring datum, we also offer a macro to declare the same atom in a more compact form. So this is a pure syntax sugar to make it easier to write atoms. The reason there is benefit for doing this because if in the future we have to make an API change, then if you write your atom in the plain vanilla Julia code, you have to make corresponding changes if there are future API change. But if you use a datum macro, then we're just going to modify the datum macro in one place, and all the datum you declared using this macro don't have to be changed. So there is a benefit of doing it using the macro, so it's recommended. And then we declare another datum, which is just a random data frame with a different mean value specified as the first parameter. So in this case, this is pretty much all the syntax we have for the datum. It's pretty straightforward, and I don't think require any further explanation. The one point I want to just emphasize that the atom interface is implemented in all major programming languages like Python, Java, .NET, R, like what have you. So make it very easy to interop with the libraries coded up in other programming languages, or plug them. You can easily plug all of them and mix match them in the graph. So this part is really the key part I want to explain. This is the RuDSL syntax that defines the Fibonacci type of operation on random vectors. So in this case, as you can see that first we use this another Julia macro add rules to define the RuDSL. It takes a namespace. In this case, namespace, you can give it any name. We call it sequence, SEQ. So after the namespace is a begin end block. Within this block, you have a isolated number of declarations of your rules. So we call these basic logic unit rules. So pretty much, if you look at the syntax, for example, if you look at this core recursion definition of the rule DSL, this part specifies the output node, the name of the output node. It can take parameters and it can take this like a value-based templatized types. So basically, the output node is fully it can be parameterized with different types, and inside you can have a begin end, or if you just declare one line, you can drop the begin end. So this part ties the output to a particular atom. So basically, this says that the operation to be applied in order to generate this output is captured by this atom. And this atom, the square bracket syntax, will be directly translated into a parenthesis at runtime, so that the constructor of that atom will be called. So therefore, when you change the square bracket to parenthesis, this gives you a direct way to create that atom as part of the graph. And then this the atom is followed by a list of the upstream dependencies of other nodes in order to create that atom. In order to create that output node. So in this case, just the two previous terms of the Fibonacci sequence. It's very straightforward. As you can see, that the rule syntax support recursion, and also in this case, the second parameter basically identify whether this node is a initial condition or not. If it's initial condition, then just does something special, like we just create a random vector for the data frame. So this is pretty much the core logic of the Fibonacci sequence definition. As you can see, like it's pretty straightforward to read. There's no complex syntax features, and this pretty much captures like probably the majority of the syntax available in the rule DSL. And you can see that this is very different from traditional programming language, as ordering doesn't make a difference. So these are fully declarative syntax. So the rules are not executed one by one. Instead, at the runtime, we're going to recursively take one of the rules and expand its upstream dependency recursively, so that the entire graph will be created on the fly. So the other two rules actually just for convenience. So if a user didn't specify whether this is an initial condition or not, we just automatically insert it. In this case, the 0 and 1 are the two terms that are initial condition. And if the user give a floating point number, we just cast it to an integer and call the other rules. So in this case, you can see that we support the polymorphism. So the different rules can have different behavior. And also, like this alias is a very useful atom that just delegate this, basically create a reference of this node to the input node. So it directly pass through, allow you to organize the rules in a more readable manner by assigning different names. So this is pretty much all the syntax, the majority of the syntax in the rule DSL. As you can see, it only takes like probably 10-15 minutes to explain. It's a very minimal syntax, doesn't have any of the complex language features. So then later on, we can see how these rules are used to create the graph. So in this case, for example, if you want to create a Fibonacci sequence node with parameter 3.2, so what we do is use a fully qualified name with both the namespace and the rule name. So in this case, map to this rule. And we use this macro to bind a concrete parameter to this rule. And once we bind it with a concrete parameter, it becomes a node ref type. So basically, a node ref is nothing but a rule with every parameter binded with concrete values. So this uniquely identify a node in the graph, because there cannot be, if you have two nodes with same rule and same parameter, they are the same. It's really the same node. It should only exist once in the graph. It should not have duplicates. So we guarantee that there's no duplications. And this is pretty much a very straightforward way of assign names to all the rules in your graph. It's tied to the rule DSL definition. It's very convenient because it allows you to name any arbitrary rules and nodes in the graph. So once we have this reference defined, we just call these two functions to get a graph output, and the result is showing here. So we can also bring up a graph UI. So this is a very convenient interactive web UI that will allow user to visualize step-by-step how the data is produced and how they flow through the system. As you can see that this pretty much like straightforwardly follow the rules. So first we have a rule defined for floating point number, convert to integer number. Then we have that integer number depend on a version with two parameters, which is now the initial condition, and it continuously get expanded. Eventually you hit the initial condition. It's very straightforward to define the graph like this. Also in the graph UI, we have also can look at the rules, the dependency of the rules. So these are really the relationship between the four rules we have specified earlier. This gives a convenient view of your computation logic and also the underlying rule declaration the developer has written. So yeah, we already mentioned that this part. So once we have the node ref, it's uniquely name a node in the graph. We also can take a hash of that node ref to produce a unique ID of the node, so that the node can also be uniquely identified by the hash ID. So in this case, for example, if you want to directly query these two nodes, we don't have to search the graph, traversing the graph, can just directly run them by pick up the names and directly ask what is your value. So in the next part, we're just going to show how to handle dynamic number of dependencies, because sometimes the number of upstream dependency is unknown when you write the rules. It could depend on your parameter, or could depend on some other intermediate calculation you do. This is very like a rich. We want to support this type of rich dynamic behavior. So for example, in this case, if you want to compute all the even terms, the summation of all the even terms of the Fibonacci sequence, we have this language. We have this like a syntax support of 3 dots to specify dynamic dependency. So basically anything before the 3 dots have to return either a node ref or a vector of a node ref. So that node ref or vector of that will be taken as the dynamic dependency of this node. So for example, in this case, when we declare we want to have all the even terms summed up, the dependency on the previous node is a variable like depend on the number of n. So in this case, for example, if you look at if you have n equal to 5, in this case there are 3 values. So this entire vector will be replaced as the dependency of this node. So as a result, using this syntax feature, we can create a dynamic dependency like this, like sum up all the even terms of the Fibonacci sequence. Also, like you can declare local variables between the beginning and end block. So this time, sometimes this can be convenient if you want to do some quick data manipulation processing before you return the datum definition and dependencies. So yeah, this is pretty much all the root DSL language feature I want to introduce. So probably it hasn't covered everything, but it covered probably almost 90% of all the syntax we offer in the root DSL. Just a quick word before we move to the next session. As you can see that these declarations directly map to the graph construct. That is why it's so convenient and so efficient for creating large graphs. As you can see, it's structurally, it's like output node, upstream input dependencies, and what you want to do in order to create that on this node in order to create that output. So even though this syntax is very limited, very minimal, but you can see that it can handle polymorphism, it can handle recursion, it can handle loops. For example, you have a handle branches. So in this case, we do have different behavior for initial terms or non-initial terms. All of these rich language feature you may think you need, actually, we have shown you don't need any of those. You just need this simple plain declaration of rules that follow the structure of the graph, and you can do everything you could do in the traditional programming language. So the next part, we're going to introduce yet another very important concept called runtime and graph data. So far we have covered the root DSL syntax and how we can use it to create graph logic, and also how that can interface with Atom and to interface with your traditional style of programming using functions. So just having the logic completely defined is not the full story of enterprise system. So any enterprise system have a rich set of configuration for runtime. So for example, whether you want your enterprise system to be like your system to be distributed, whether you want the intermediate results to be cached, whether you want to compute AAD along the way, or whether you want to run the entire system in a batch or streaming mode. These runtime configuration are not covered by your business logic or your analytical data logic. These are really how you want to organize, implement your system for the runtime behavior. So what's tend to happen is that, for example, in large banks, for example, since if you take streaming and batch as example, since these two different configurations have a very different requirements. Of course, streaming application wanted to be fast, and batch job you want to be like a scale and really process large number of trades very quickly. So we end up with often building like two separate systems for batch and streaming because their runtime behavior is totally different. So in this case, even though their logic ideally should be, their modeling and analytical logic ideally should be different, but they have separate implementation. That duplication drive up cost and make it difficult to support. Oftentimes your batch system and streaming system can go out of sync because they may follow different update schedule, create all kinds of problems. So in this portion, we show how Julius graph engine handle this problem generically. So basically, besides root DSL and Atom, that is really the two constructs you need to define your entire business logic. We also follow the we also offer another construct called graph data. This really encapsulates all the runtime configuration behavior you may want to do differently on the same logic. So here we support the three runtime configuration out of the box. They are all subtype of graph data. So far, we have been showing the usage of generic data. Later on, we're going to show a example of stream data. So the generic data is really like a batch configured for batch job. It by default have all the intermediate results cached. That is why when you go to the graph, you can see all the intermediate results at your fingertip. Become very convenient. So the stream data is really configured for streaming use case, and the numerical data. This is for the special use case of adjoint algorithmic differentiation or AED. So if you want to compute AED in your end-to-end system, you're going to use the numerical data. It is have native AED support. So also another point I want to mention that you can derive from this graph data and implement to your own runtime behavior. So for example, you may write a runtime behavior that doesn't do caching or doesn't do some of these things, or it's completely up to the user if they want to have a different use case other than the three we support out of the box. So the next portion is really showing how easy it is to take the Fibonacci pipeline. We build a very simple pipeline, turn that into a streaming job. So in this case, to make it more useful, we implemented atom that simply compute the rounding average of all the data frames that are seen at this point, and we can connect this new data using a rule. So basically, says that I want to compute. I can compute any nodes. I can connect to any nodes and compute its like a stream average. In this case, this is a very interesting rule because as you can see, take a node ref as a parameter. So if you recall, the node ref is nothing but a particular node in the graph. So this actually declare a generic pattern says that this rule can apply to any node in your graph and compute its like a rounding average if you're running the streaming mode. So this is another like very useful feature of Julius rule DSL, which are called high-level rules. So you don't have to declare like always declare concrete rules, but you can also declare generic patterns. So in this case, it's a generic pattern that you can basically connect to any node in the graph that does its thing. And this part, we specify how the streaming should be sourced. We take the first two initial terms as a source of streaming. Then we basically say we have the fifth term, and we are going to connect this streaming rule to that node, and we're going to run the streaming process. So as you can see that to convert your system into streaming, only need a few lines of code change, specify the runtime configuration, then you get a streaming system. In this case, we stream like 20,000 data frames through, and it's very fast. Like 10,000 data frame only take 0.8 second. You get the average of these 10,000, running average of these 10,000 streamed data frames. Oh, sorry, 20,000 actually streamed, 2 batches of 20,000. So in this case, it's effectively we're computing the fifth terms of Fibonacci sequence using the Monte Carlo simulation. If you look at this end to end, so now we can look at how we can bring up the UI, and this is the output of the streaming. As you can see that the last node, this is the running average of all the previously streamed nodes. And if you look at the previous node, this is the value of the last data frame that has been streamed through. So therefore, the cumulative effect are showing in the last node, and the rest of the graph only caches the last value it has seen. So this is pretty much like the key highlights I want to go through for rule DSL, and a very simple use case of Fibonacci sequence, and also how to turn that into a streaming use case. So basically, the takeaway here is that really the syntax of rule DSL is very simple, and it doesn't take much effort to learn and use, and also it is very flexible. It gives you the ability to quickly turn your system into batch or streaming mode. Later on, we're going to show how to use distribution in the next part of the presentation. So by now, I'm going to stop sharing my my screen, and let's see if there are any more questions coming from the Pigeonhole. Okay, so there are a few questions. Let me try to quickly answer them by the order of hopefully upvotes. Out of curiosity, is the name Julius inspired from Julia? Yes, yes, the name does come from Julia because the root DSL is implemented on top of Julia as a sort of macro layer, and also we do like rely upon a lot of these Julia language features, such as the multiple dispatch. Okay, so okay, some of the question has been answered by my colleagues. So is Julius hiring? Yes, we're hiring. Where is the root DSL repository? So currently the root DSL repository is a private repo. So therefore, like if you log into our website, a free developer website, you can have full access to the functionality. There's a question about how easy it is to reorder sequence. Okay, so I think these are probably specific questions. We'll leave it. We'll answer offline. So the next portion of the workshop, we're going to have. We're going to go through a machine learning use case.
Hi, can you hear me? Okay. Hopefully you're hearing fine. In this part of the workshop, I want to talk about machine learning with Julius Graph Engine. And well, for this, I will share a tutorial on which we are going to solve a basic machine learning workflow. So hopefully you're seeing my screen now. Well, here we are going to be solving the Titanic dataset, which is a well-known machine learning problem to predict the survival of the passengers of the Titanic. And for this, we'll be using the predefined rules and atoms available at the Julius data science package. And we will see how these rules cover operations such as data loading, visualization, and transformation. And then we are going to see the great capability of integrating with another language, since we are going to train the available Python models. Then we are going to use a higher order rule to measure the performance of multiple models and to tune the hyperparameters of said models. So hopefully that'll be really interesting. The first thing to do is configure the workspace, importing the libraries that we're going to use. And here's some Jupyter workspace configuration. And the first thing to do, we declare the config variable that is needed at the moment of the graph creation. With this parameter, you can set a project name. In case that you need to run more than one graph, you can identify the graph associated to this project with this parameter. So let's begin and load the data. For this, we are creating our first node reference here through the rule DSL reference macro, and we are referring to the rule DS namespace. And we have two rules that support the loading of data. In this case, I have my data on a CSV file, but also we could load from a URL. And these parameters here are actually passed in the background to the csv.jl read function, which returns a data frame with the Titanic dataset. And this is the name of my file, and this is whether it has headers. And with this parameter here, we are setting a label for this node on the graph. So it will be easy to identify. So next, we want some information about our data in order to know what we need to do to work with it. And for that, in Julia and also in Python, in pandas, we have the describe function, which gives you statistics on the columns. So here, this rule, data summary, what it does is to take another node reference, and it will apply the describe function to the output of this rule. In this line here, we are creating an instance of a blank graph with our configuration. And in here, at the calc forward call, we are computing this graph. Here we indicate the name of the instance we created. And here we pass like this the final output of the graph, the final node, which is this one, the last we declare. And since every node must have information about the predecessors, about the dependencies, the graph can be computed recursively. Now, once the graph is computed, we can get data from any node that we want with the getData function. We specify the name of the graph and the name of the node that we want the output. And since every data must return a vector as an output, here with the 1, we indicate we want the output that's inside the first element of that vector, in this case, a data frame. And this is the result of applying the describe function to the Titanic dataset. We have the names of our columns and some statistics. And the first thing to do, we analyze this and see that we have missing values, and we need to fill those in order to work with this. Well, maybe Kevin here has too many missing values. This is most of our data set missing, so we are not trying to infer this variable. We are going to drop it. but we are going to fill embark and age columns. And for this, we have the fill missing rule under the DS namespace again. And this rule takes a node reference and a dictionary with the names of the columns we want to fill the missing values as keys. And here the values of this dictionary is the function that we want to apply, the method that we want to apply to this column. And this will operate over the whole column and fill the missing values with the result. We use the same rule as before, the data summary, to compute a summary of that. And we see that the missing values of embark and age are both gone. And well, now we can maybe analyze atypical values or things like that. But let's say that our data cleansing is done and proceed to feature engineering. And for feature engineering, well, we want to select the features for our models to train with. And for example, we may want to create new columns from the existing ones. So in this case, we have the fair column, which is a numerical one. And we want to normalize it, for example, subtracting the mean, dividing by the deviation. And now we have a new distribution for our fair column, centered in 0 and with 1 as a deviation. Another thing we may want to do is reduce dimensionality. For example, in this case, this column is the amount of relatives a passenger has. This column is the total amount of relative a passenger has on the Titanic, since this represents the total amount of siblings and this the total amount of parents or children that are on board.
Sorry, Milena. Some people are asking to enlarge the screen, so if you can zoom in a little bit.
Oh, sorry, I wasn't really seeing. Maybe that's too much. Is it readable now?
Yeah, I think it's much better. Sorry
Thanks.
for that.
Okay, maybe can hide this as well and maybe enlarge a bit more. I don't know. Okay, thanks, Maro. So the next thing, after we declare this as a quotation, here we have two expressions with some information about the line of declaration of this code as well. And these are the new features that we are going to add. Then the features that we do not want to use, we need to declare inside of an array as expressions as well. These are the names of the columns that we are going to drop. And if we want to transformate a data frame, we can use the call transform rule that allows us to pass a node reference with our data, then set a name for our operation, and then pass the new features and the drop features. And here we will have a node reference with our new data frame. We will compute a data summary again from that node reference. And we can see that now our new columns are here. Probably should have dropped these 3 as well to reduce dimensionality, and since now we are creating the new ones. But let's continue like this. This is an example. Here the mean is now 0, and this is the sum of these 2. So now we can compute our graph and see the whole workflow through the nodes information. And what's interesting here is that all the input and output of each node is cached in memory. So with the code of this cell, we can here pass the name of our graph. And we can visualize it through the Wave UI much better. And slow it. Ready to load. Yeah, of course, I also should check on the questions. Sorry, allow me to rerun all of the cells again. This is kind of laggy, probably through my internet connection. Let's access again to the tutorial. And I run all of the cells. Okay, there's the server running.
Yes, you can run all the cells again, Milena, just on the
Yes, I think right now they are running. We are going to go through this again. Really sorry about that. Probably had my kernel going for too long and people is connecting, so you can always restart the kernel if you encounter an error like this. Another thing to mention is, for example, if you change a definition of a rule of a graph, it's a better practice to restart the kernel and run everything again. So now hopefully it will load. Great. Now we see our first node declaration that is here. And here we can see the atom that's applied to this node. In this case, it's alias. The alias atom allows us to refer the output of a different rule. In this case, we are referring to this one that is performing the creation of an atom that outputs the data frame that we passed. Then we made a summary of that. Then we fill the missing values, and you can always see the output here. Then a summary, and then again feature engineering and a summary of that. So it's really easy to trace and debug what data we are going to use to train our models. Here we have everything is cached for every node, so it's not like you run these ones and then you don't really get explainability on why your model gave certain results. You can always debug really easily like this. And the next thing to do is to train our Python models. And for that, I want to present this PyTrain rule, this PyTrain atom that works as an interface with Python. Here you can pass a full name of a Python class to use. And here the options is a dictionary with the arguments to that Python class. And this step is creating the atom and a structure with these fields. And at the moment of the computation, we call the forward data function of an atom, and we pass the training data. And since the rule DSL supports multiple dispatch, here we can use polymorphism to define different behavior for different type or for variable. In this case, we have the classifier train rule that will call the desired PyTrain atom that we want to use, depending on the model that we want to train. So now we will see a higher order rule that will allow us to train all of these models at once and measure the performance on different metrics. And for that, first we need to declare a classifier spec object, classifier spec variable that will contain data about the models that we want to train, and also about the x's and the y's of our problem, and also some indexes used for validation and training, and the name of the target column. So first, we declare all of the models that we want to train like this as pairs, indicating the dictionary. This will be then the options variable here. So these are arguments for these Python models, all in scale-learn library, as you can see here. Also XGBoost. Then we are here declaring our target column. Here we want to select a portion of our data to use as validation and some other portion to use as training. So we can take a node reference, which is our clean data, and here select a fraction of the code that will be used for validation, and the rest will be used for training. So with all that information declared, we can create our classifier spec variable structure, passing the models and also our clean data. Here, notice that we are only passing the clean data, and the operation that we want to pass to it is passed separately on a tuple. Here is the name of the transformation we defined earlier and the new features. Also, we are passing the name of the target column and the validation indexes. So at this point, it's really easy to define different classifier spec objects, for example, to train different models with different transformations. So it's really easy to reproduce multiple experiments with this. Then here we define an array with the metrics that we'll be using and create a new node reference with the classifier metric higher order rule. This rule will take our classifier spec object with all of the information of the models and our problem. And then we'll compute a dependent node for each one of these metrics here. So we can compute the graph with this node that we declare as a final output, the classifier metric. And we see here that this is all the time that it took to train all of the models and calculate the performance. So yeah, here all of the necessary classifier train rule has been called. And if you want to retrieve a result of the graph, you can create a node reference. For example, this node reference is a dependent node from this one, as this one calculated each one of these separate. So you can instantiate a concrete instance of a node and then search it on the graph with the get data function. And if we see the output of this, here we are just computing all of the output of this node. That if you check, this is a dictionary with both in-sample and out-sample metrics, and both point to a data frame with the metrics for each model. Here we are computing all of the metrics together in a new data frame. Well, as expected, we have much higher performance for the in-sample metric that is using the training data to predict. And this is how all of our models perform. Already they are trained, and we can see that how that happened through the graph. So here we have our data loaded. Here we made the missing values imputation, and we passed that clean source of data to our classifier spec structure. And here it just managed to do a split of the columns in the x's and the y's. Here you can see it saves the x's and the y's by separate. It applied the feature engineering to the x's and then numerized the non-numerical values to train the models. Then again, we use our clean data to select a random number of indexes for validation. And those indexes are used to split the data for training and validation. Here is where the model training is happening. And here we are computing the metrics. And what's really nice here is that, for example, you can define, as I mentioned, multiple transformations to train multiple models. And it's really easy to see what one model is being trained with. Because, for example, you can select show precedence. You just right-click and show precedence. And you see the full lineage of this node. So now it's really easy to trace all of the workflow and debug how your machine learning model is being trained. Then let's continue. Here we see that we can compute the total amount of nodes on our graph. There are 83 nodes. And now let's use the higher order rule hypertune to tune the hyperparameters of a desired model. Here we are creating node references to tune all of these models. We are passing again our classifier spec structure. And here we could pass, again, a dictionary with the arguments for these models in case we want to fix a hyperparameter or pass another argument. Here we are selecting the metric, and here the last argument is the hyperparameters that we want to tune. So here we will perform a grid search between these values, going 50 by 50, between 50 and 200 for the numbers of trees computed in this case. And like that, this rule will return the metric performance for each one of these combinations. Here we are just declaring another node reference that aliases. As we have seen, the alias atom just references the output of another node. Here we are referencing the output of all of these nodes. So if we compute our graph with this final output, recursively, all of this is going to be computed. And here we select, for example, we see that we created a new graph. And here, for example, we are calling to this dependent node, which is this one, the gradient boost model. So we are going to see the performance for that for all of the hyperparameters that we wanted to sweep. So here I'm not going to dive deep on which perform best, but we could say, for example, that we want a similar value between the in-sample and out-sample metrics, because a wide difference between these may mean that it's overfitting too much. For example, this one is widely different from this out-sample metrics. So for example, this one here may be better. I don't know. You should analyze this well. And then we can see our final graph on the web UI again. And this looks much simpler than before. We see that our classifier spec creation is the same, but here we should be training our model since we created a new graph with this output. So if we actually check at these nodes, we see we have an inner graph that we can inspect. And we see all of the training of the models is actually contained inside of that graph, inside of that node, sorry. So for that node, actually, this was the input and this was the output, and all of this was hidden on the background. So it's really easy to finally trace all of the input and output for each one of the nodes. Finally, as a conclusion, we can say that we are provided with rules that allow us to solve a machine learning basic problem. But of course, you can also define your own rules and your own atoms with your desired statistical operations or whatever you may need. And you can use the low-code macro syntax to add new rules and atoms. Also, it's really easy to debug our models, get some explainability of the results we have, since once you run the graph, all of the workflow data will be there, cached in memory for you to check. And also, it's really easy to reproduce multiple experiments with multiple transformations, different transformations, and those are really useful tools for this. Also, there's to remark that you do not need to throw away your work in another language, or you can use another language's really useful libraries, since we provide the capability of creating atoms that work as an interface, as mentioned, with another languages such as R, Java, C++. In this case, we see that we are provided with an atom that already allows us to train and model on scalearn on Python. And also, this scales really well. Probably one of the most important features is that you can connect your machine learning pipeline to a really high, a really large scale data analysis. For example, you may have a really complicated data gathering process, for example, or you may want to predict something that's happening live. And for that, you can stream data, really integrate your machine model training and prediction inside a full data pipeline. So that's a really useful tool to remark. Well, next, my colleague Mauro is going to explain how to distribute a task, which is useful, for example, in cases that your data does not fit into your memory, or that you want to use capability of multiple machines to perform a task. So we are going to see how to distribute. Thanks for
Milena.
listening.
Thanks, Milena. We will give some seconds in case there's a question regarding this last talk. So you can also use Pigeonhole to refer your questions there, and of course we will be answering. Okay. So let me start sharing my screen. Please let me know if you hear me well. Okay, cool. Awesome. Okay, so I will start now. Thank you very much, all of you. My name is Mauro Coco. I'm part of Julius' team. This talk will be about how to build a MapReduce generic pipeline by using our rule DSL. So to summarize briefly how this talk is going to be organized, first we will do an introduction on the MapReduce programming model. Then we will jump onto our Julius web server and we will start building just from scratch a generic pipeline. And we will use a word count example to guide ourselves on how to build it. Then we will show also some other examples on how to reuse this generic pipeline to tackle another problems. In the end, I will be showing how easy it is to make distribution based on the same code we will develop together. So let's first talk about MapReduce problem. This is a programming model that was first introduced by two researchers on Google in 2004. This was discussed under a paper called MapReduce: Simplified Data Processing on Large Clusters. So I don't know if you are all familiar with this, but I will try to explain it as best as I can. So this is a strong a programming model strongly oriented to parallel and distributed execution, which is particularly good to tackle large amount of data and computing. And it is built to be simple, fast, scalable, and fault resistant. The first implementation of this was introduced to Hadoop, so you can find the implementation of MapReduce on these tools as well. So what's the idea of the MapReduce programming model? So the idea is that you can split your data source into multiple batches, and these multiple batches can be sent to several workers. So the idea is that when you apply a MapReduce, you're usually thinking on a cluster context of multiple machines. So these first workers will apply a mapping function, which is common to all of them, and it's going to be applied to every batch of data. Then a shuffling process will occur, which it's basically redistributing the outputs of the mapping process based on certain keys that must be provided at this step. And in the end, the output of the shufflers that have organized the mapping output based on the keys, this output will be applied with a reducing function, which will basically apply the same process to all of the batches and finally give us the final output. So at this point, this sounds very abstract, and let's see how this looks with an example. So imagine you have a large collection of files with many words on them, and you want to apply this MapReduce pipeline to count the number of occurrences of each of the words in the document. So you can start with a data batch like this one. You will split it into several batches. Then you will send to these batches to the workers, and you will apply a mapping process to all of them. So in this case, the mapping could be just generating a vector of pairs, where each pair is going to be the word itself and a number 1. Then the shuffling process will combine all the same keys together into a single node, and this node will be transferred to the reducers, where the counting of the number of occurrences for each word is going to be occurring. In the end, the final result will be prompt as a single node. So I'm going to recap a little bit on the syntax of our rule DSL. So let's first focus on how to define the rules. So we are going to be using this add rules macro, where we provide this namespace, which is particularly good for organizing our rules and avoiding name clashing among them. Then we define the rule name, we define the rule arguments that it can take, and we can define now the body of the rule. So here we can add some additional code to make transformation, for example, to the rule arguments or whatever you need. And in the end, you must provide an atom. So you provide the atom name here, the attributes that this atom accepts, which are basically the attributes of the structure behind the atom. And then you must provide the dependent nodes here between parentheses, which are basically nodes based on other rules. Okay. So the atom itself is going to be the responsible for processing all the data that is given here on the dependent nodes. Okay, so the idea here on this talk is to build a rule like this one we have here, which we will call MapReduce, and it's going to accept the batches of data we will provide. Then it's going to accept a generic mapper, and then a shuffler as well, and a generic reducer. Well, we will see how to make the definition of this rule. So here it's important to mention that this rule that we are going to build, all the dependencies, all the arguments here are of type rule DSL node ref. So it's important to mention at this point what it's a node ref. So it's basically a data structure that refers to another node in the graph. Okay, so we need to mention that every node in the graph is created by a specific rule. So the dependency here on another node can be understood as the dependency on the underlying rule. So a rule like with a node ref parameter or many of them is called a high order rule because it defines a generic pattern whose behavior it's going to depend on the other rules, yeah, that you will be defining here. So this is extremely powerful in order to define abstract and high-level logic and behaviors. And this is, for example, what we want to do at this MapReduce pipeline. So we can also pass a high-order rule as a parameter to another rule, and this can lead to creating even more higher-order rules. So it can be as abstract as you want. So this ability to nest high-order rules is one of the reasons why the rule DSL is both low-code, which is one of the parts of Stellar, and it's expressive, and this is one of the biggest benefits of graph computing. Okay, so let me now jump after this introduction to our tutorials site that you can also access. And we will be working on this MapReduce tutorial, which is number 3. And in the end, I will also show a little bit the fourth tutorial, which is on distributed machine learning, which is basically reusing this pipeline we will build together.
Mauro, you may want to hide the message on the bottom of your screen. StreamYard is sharing your screen. You want to hide that? Yep, thank you.
Thank you, Yadong. Okay, so you can still go through this introduction yourself, and it's basically explaining what I've been showing before. We'll start from the generic MapReduce here. Let me enlarge it. I think the size of the screen, it's okay. So let me know if it is too small. I will enlarge it. So the first thing we need to do here is to start defining the mapping process. And we will start guiding ourselves through this word count example. So imagine you have a sentence like Mary has a lamp. And the mapping process for this particular problem will be transforming this into a vector of pairs like this one we have here, okay? So along this talk, we will be using this apply function atom, which is a really handy atom that can accept a particular function and its parameters, and then apply this function to any kind of data that is related to this. So this apply function atom is defined on data science package that is on Julius. So you can use it whenever you want. So the idea now is first we are going to load our libraries, and we will define the word map function that is basically transforming the sentence into a vector of pairs, like we've said before. And the rule here for the mapper, it's going to accept a data batch that is going to be a node ref and a mapping function, which in this case, for the word count example, is this word map function here. So you see, we use the apply function atom. We provide the map function as an attribute for it, and then the data node ref is provided here as a dynamic dependency. So by doing this, we can imagine you already have defined the several batches here, and we'll see how we can define that. So for each batch there, you can create a node ref based on this mapper rule we have just defined, provide this batch as an argument, and then the mapping function, which in this case is word count. And then we can define another rule, which is MapReduce, which can take all the batches, all the mappers, all the shufflers, and reducer. So this could be an approach for this problem, but it's actually problematic because it's putting much burden to ensure the consistency, because we have to define all the mappers, all the shufflers, and reducers, and each of them are based on the previous one. So it's gonna be easier to build it in another way, and we will see how we can do that. So the mapper, it can be defined without passing the first argument. And that is because we can use this prepend function that is defined here, that allows us to put the first argument, that in this case is the batch of data, later on when doing the MapReduce rule definition. Okay, so this idea of avoiding passing the first argument to the mapper, shuffler, and reducer will be used along this tutorial, and the data batches will be provided at the MapReduce stage. Okay, so let's now define our batching rule. So this batch rule will be accepting, for example, a sentence, and then we will use the apply function atom again. The function that we will apply to this is just the identity. So this is basically transforming a sentence into a node ref. So it will accept the sentence here as an attribute, because it's not a node ref yet. And so here we will start, for example, defining our data source, which are a tuple of sentences. Then we define our batches from all the sentences, and then we can define this mapper node based on the mapper rule, but you may see that we are avoiding passing the first argument. So to note that, we are using this underscore notation, which basically means that we are not passing the first argument to them. So we can now use the prepend function to illustrate how we can use it to pass the first argument to our mapper. So we can create a vector of node ref by using the mapper rule, using the prepend function to give this input for each batch. So we can run all this, and here this particular code is just for transforming the node labeling, which is really good to have a better understanding on the graph. So I will not enter into the details of how this is written, but you can take a look, and it's really handy to do this. So here the node has been built for this pretty simple task, and you can take a look on the Jupyter notebook, or you can go to the web UI as well. Yeah, I will run again all this, because after 15 minutes it's going down. So I will restart the kernel and run all the cells. Sorry for this. Yeah, so now we can see it. So it's a pretty simple graph where we have defined the 3 batches, and then the mapper have been applied to each of these batches. So you can also see the information here, and it's pretty simple. Okay, so after the mapping process, we have to define the shuffling process and then the mapping process as well. So I will not now enter into the details as we have done with a mapper, but I will mention briefly how this is built. So the first thing is that the shuffler needs to take the output from the mappers and split them into multiple chunks by certain key values that have been computed in the map data. So in our mapping process, we've said that for the word count example, the keys are the word themselves. Okay, so we have to shuffle and combine all the same words together into single chunks that they then can be grabbed by the reducer. So we have to move these chunks around that so all the data with the same key is gathered together, and we have to concatenate all the chunks at the gathering node to recover the full collection of data. So we need to define this split by key function, which we have to provide here, which is the key function we are using. So which is the function that applied to the mapper will extract the keys. So we'll see in our case it's pretty simple. And by using this function, we can define a split by key rule, which is based on this function. Then we can define a select key node and a merge by key node. So these 3 nodes are pretty simple and are going to be used here on the shuffler. So all these 3 rules defined previously are used here, and they basically are doing exactly the same process that we have described here on top. Okay, so you can later take a look into this. It's not complex, it's pretty similar to the mapper. So now we can define our shuffler node based on this rule, and we will provide the mappers. So this is the input for them. This is the function we are going to use to extract the keys from the mappers. So the first function is taking the first value on a pair, and remember we had vector of pairs where the first argument was a word. And here, this is a limitation at this point. We have to provide all the keys that can appear on our dataset. And why is the limitation? Because we can know beforehand which are the several keys that may appear in our dataset. So bear this in mind. In the end of this part, we will see how to deal with this, and we will completely solve it. So now, just to make it easier, we can see this graph in our web UI and see which are the additional transformations and nodes we have added. So the previous step was finishing here on the mapper, and now we are adding this shuffling process, which are these 4 stages here. So the first one is splitting the mappers by keys. Then we are selecting by keys and combining all the results together. So you can see words are grouped together here, and then they are returned as a final result. But the reducers that we are going to define now will start from this one here. Okay, so bear this in mind. This node will disappear in our in the following graph I will show. So the reducing step is pretty similar to the mapper. We are going to define a reducer rule, which will take the output of the shuffler and will accept a reducing function, which in this case, for the word count example, is nothing but counting the number of occurrences of the word on the shuffler. Okay, so we use the same apply function atom, and we provide the shuffle as a dynamic dependency again. So for the word count example, here we define the reducing function. It's a really simple function. And now we are able to define our MapReduce finally. So this rule will accept the several batches we can define based on the batch rule we defined previously. Then it will accept the mapper, shuffler, and reducer in the way we define with an underscore. Okay, so avoiding passing the first argument. So inside the rule, we will use the prepend function to pass the first argument to it. Then we will use it again to pass the mappers to the shufflers, and then we are going to use the same prepend function to pass all the shufflers to the reducers. And then we will combine all the results into a single node by using the merge function. So now we can define with an underscore the shuffler, mapper, and reducer. So here you may see there's no data being passed, but the first function and the keys for the shuffler, the word map function for the mapper, and word reduced to the reducer. So this definition is pretty simple. Then we define the MapReduce node, and here we pass this the batches, the mapper, shuffler, and reducer, as we mentioned before. So we can now create the graph and run it, and we can see it on the web UI. Okay, so we mentioned here it's a mapping process. This is a shuffling process up to this point, and now we are applying a reducing operation to each of these batches, and we finally get the final node here. Okay, so these reducers are just counting the number of occurrences and returning it as a pair. So as I mentioned before, the limitation regarding the shuffler was that we needed to provide all the possible keys in our dataset, and that is impossible in a real application. So the way of solving this is by using the hash and remainder functions. So we mentioned that we needed to provide a function to extract the keys from the mappers. We were using the first function, and this first function can be then hashed, and the output of this hash can be used to apply this remainder function with a particular number that will give us the number of shufflers we are going to use. And why is that? Because while applying this remainder function, the possible values that we will have are the collections here from 0 to 2. So if you apply the remainder function with 3, so the possible values are 0, 1, or 2. Okay, so imagine you have a value n, then the possible values are from 0 to n minus 1. Okay, so this is how we can solve this problem, because we still use this first function, but by using the hash and remainder function together, we know which are the possible keys that that are going to be used. So let's now take a look on how this graph looks like. And you may see now the difference is that previously we were selecting by the words themselves, but now we are using the select. We are selecting by these integers. Okay. So as I mentioned before, the number of shufflers now are 3, because that's the argument we have used for the remainder function. So this can be later on passed as a parameter. So here you can see, for example, that this node, that 2 words are going to the same node. So the reducer function needs to deal with these 2 values in the same node properly. Okay. You may see this reducer function is well defined, and the MapReduce node has the correct answer as in the previous example. Okay. Okay, so now we can redefine our split by key rule here, and we can redefine it by using our hash and remainder functions. And you may see that here the argument n is provided, so you can select the number of shufflers you can use. Okay, so any questions up to this point? Okay, so I will now show you how to apply this same MapReduce pipeline to solve another problem. And another interesting problem is the finding friends problem. So imagine you have a social network where you want to know which are the common friends between 2 specific users. So you may have this information here. So imagine you have users A to E, and you have this information for each of them. So you have, for A, you know that the friends are B, C, D, and for B, you know that the friends are A, C, D, and E. So if you want to find the friends in common for each of them, you may see that if you only count with the information of A, you can say that the friends in common between A and B may be C and D. And if you see the information from B, you can say that the friends in common are C, D, and E. Okay, these are the possible values for each of them. So the mapper, to solve this problem, needs to take into account which are the possible values for each of the friends based on the information on the users. Okay, and then so this is defined here on the mapping function. Yeah, you can then take a look on how this is built. And the reducing function is basically computing the intersection of these sets, of these subsets. So you may see that the correct answer to find the friends in common between A and B is the intersection between the subset CD and CDE. Okay. So you can use these functions to define your mapper and reducer. Then the shuffler will use the first function as well, and we can run this whole graph and see the output. Okay. So okay, so now you can see the graph. I will go into some details to highlight how this works. So you can see that in the mapping process, for each of the friends that for each of the users, sorry, that are the several batches, you apply a mapper and you compute which are the possible friends in common that a friend and these users may have. Okay, so you compute that for all of them. Then you split by keys and you combine all together here on the shuffling process, and you apply the reducer to take the intersection of these outputs. And then you combine all the results together in a single node, and you may see here for A and B that the result is correct. The friends in common are C and D. Okay. So let's go back. So here it's another example. It's a group by example. I will not show it now because I prefer to save some time to show you the distributed machine learning pipeline briefly. But you can take a look. It's basically the same logic applied. You have to define a mapping function and a reducing function, and then you can solve the problem. So the good thing about this pipeline is that the user only needs to think about which is the mapping and which is the reducing process that they need to apply to solve the particular problem they are dealing with. Okay, so yeah, you may see here it's a graph. Okay, so now before showing how we can make the distribution of the previous pipeline, let me talk about some advantages of Julius graph. So in particular, I want to make some comparisons against function composition, because you may find some similarities between high order rules in our rule DSL with functions with high order functions in languages like Haskell, for example. So the first things I want to mention is that while using high order rules, this doesn't create typical stacks, and the result is nothing but another graph. Okay, so this ensures that to the developer to visualize and debug to be a really easy process, while if you are using a function composition, you need to use a debugger to access the intermediate results and call sequences, and this is a much complex process to do. So another thing is that the resulting graph composition can be automatically distributed without any code change. And you will see that this is really easy just in a few minutes. If you want to do the same with traditional functional code, this is not really easy to make it automatically or efficiently at the same time. Then the graph composition is much more flexible. So once you build the graph, you can run it in different modes, like Yadong explained before. So you can use both batch and streaming modes to basically the same case without many code modifications. And this is basically impossible to do in this way with traditional functional programming. And the last thing is that while graph compositions can mimic function composition, the reverse is not true. And the MapReduce is a good example of this. So let's now focus how to make the distribution of our MapReduce pipeline. We will see how easy it is to do this. So the first things we need to do is to define some configurations on top, but we'll not enter into the details of this. It's basically the same for any project you are dealing with. So you just have to repeat this code. And here we start our local master service, and here we define the number of workers that we are going to use. So this can be done basically on two ways. We can use a cluster with many monitors, or like in this case I'm showing, we can mimic the cluster behavior by using the several cores available on our computer. Okay, so in this case I'm going to use 3 cores available on the CPU I'm using. The code for any of these cases is basically the same. At this URL, we are going to see the outputs. This is a web UI, and the first thing is to import the modules you are going to use. So the difference here is that you need to use this macro remote deval, and you have to provide this connection to the graph. Okay, so this is a remote graph proxy object defined here. You have to provide it in order to make the connection, but the code is going to be the same. Then to add rules, you need to provide this add rules macro as we used previously, but the difference is that you don't only need to provide the namespace, but the connection to the remote proxies also you need to provide it. So after this, you can make the rule definitions like we did before, and you may see that this is an exact copy of the code above. Yeah, so any modification have been done. And then for any arbitrary code like functions or structure you may need to define, like the prepend function, the split by key, where reduce, whatever, the node labeling display. So any function can be defined by using this remote eval macro. So this is basically making the connection with the workers. So now we can use this, provide the same data source as before, create the several batches, define the number of shufflers we want to use. Here is the parameter n passed, and we can now run the computation. But an interesting thing here is that because we are doing distribution, we can let the user to say which are the nodes that he wants the distribution task to base on. Okay, so the most efficient way to distribute this, you will see it immediately in the graph, is that you can base the distribution on split by key nodes and the reducer nodes. So this is going to be distributing the task among workers efficiently. After doing this, you can dispatch all the job by using this function, and the computation will be run. Again, you can see this display here, or you can go to the web UI that was on this URL. Let's see if it loads. Otherwise, I will have to run it again. Yeah, I will run it again. Yeah, I will close all these tabs. Yeah, this will take just a few seconds because it's running all the previous computations, but eventually, yeah, it's almost there. Okay. So here it's starting the service, and then it will send all this code to the workers. Yeah, it's ready. And the computation. Meanwhile, I will restart this kernel as well, so I can show you the distributed machine learning as well. Okay. So now I can show you this. Okay. So now you can see that this is basically the first problem, the word counting problem I showed you, and the one we have used to build the MapReduce pipeline. And here you can see that different colors appear. So what does this mean? Is that each color is a different worker. So you can see that because we specified split by key to make the distribution on this, the graph have been distributed among the several workers efficiently, and also the reducer have been specified at this stage, and also the task is efficiently distributed. But of course, during the shuffling process, there's some shipment of data across, and you can't avoid that, and it's okay. Okay, so this is pretty all from the MapReduce pipeline, and you can see that we have built a generic MapReduce pipeline from scratch just by using 10 rules in our rule DSL and 20 additional lines of code for defining some functions. So here the results speak themselves. We have done it in a single core process, but then we could easily distribute it among several workers just without any code transformation. So this is one of the biggest benefits of using our rule DSL. And the last thing I wanted to show is our next tutorial, which is called distributed machine learning. And this, I will not show all this code. I will simply show you how this is built. So here we define a simple machine learning pipeline like Milena did in our previous example. We also define how to do some downsampling. Sorry, I forget to mention that this tutorial is based on this popular blog post that is called training models when data doesn't fit in memory, which is describing how to use DAGs to create a debugging pipeline for machine learning. So here we show how to build the machine learning pipeline with debugging, still without distribution. And here in the end, we show how to use our rule DSL to distribute this machine learning pipeline. But the good thing about this is that we are reusing the MapReduce pipeline, where the mapper, in this case, is nothing but machine learning, training, and validation. And the reducing stage is combining all these multiple models into a more powerful and robust model, which is basically bugging all of them. And you can also see on this tutorial that we are both using batch and streaming mode. And here it's the streaming in the end. And if we refer to this to the web UI now, you may see that yeah, the streaming output is displayed. So here you can see on this tutorial that all the mapper is this process here, which is training and validation several models in a streaming way, and here all the validations are combined, and the MapReduce is basically providing the final output. So you may see on this last node that several records of the score are computed, and here you can see that the score is getting better as you start bugging more and more trained models. Okay, so this is pretty all from my side. Of course, I'm more than happy to answer all the questions that may arise at this stage or later. So thank you, all of you, to your attention.
Thank you, Mauro. Yeah, so just quickly want to recap what Mauro has illustrated. So basically, what Mauro has shown is that you can write generic rules, and without even considering the complication of distribution. Once those rules are written, you can use Julius graph engine to automatically distribute that to multiple workers without any modification code change. That is tremendously beneficial and save a lot of time. Just imagine how you can do this in a traditional programming way. If you write a complicated function that need a distribution, that can require major engineering effort to make it run fast and optimally in the distributed setting. So again, like if you have any more questions, please feel free to ask on the Pigeonhole link. We're going to answer it opportunistically, and also hopefully we'll leave plenty of questions in the end for Q&A. So in this section of the workshop, I'm just going to show another example which shows how large-scale graph computation can be handled and distributed. So I'm going to share my screen. Oh, sorry, I'm sharing the wrong screen. Okay, so hopefully the right screen is shared. All right, so here we're just, so far we have been showing some examples in machine learning, in data processing. In this example, I want to really quickly illustrate what is a large computation looks like using our Julius graph engine. So in this case, we are showing a application that provides a large book of derivative trades. So it's 100,000 of derivative trades, and the entire graph is like more than 1 million nodes large. As you can see that the graph is too large to fit into a single page, but we allow easy navigation for the user to drill down to different parts of the graph and visualize every intermediate results if the developer want to see. So in this case, for example, you can, again, like even with 1 million nodes, you can easily trace the various intermediate results. And again, the distribution is handled generically. You haven't done anything special just to distribute this particular problem. All of this distribution capability and the lineage, like visibility, UI, all of these are generic, applied to any problem you can code up using root DSL and atoms. In this case, for example, we're using 4 different workers to distribute this relatively large graph. And you can see the the distribution is highly optimal, because in this case, you can see that there is an entire block of dependent nodes that are all allocated to a same worker. So this minimizes the data transfer between different workers. So that by clustering the relevant node in the same work actually dramatically improve the performance. The reason we can do this type of optimization is also enabled by the root DSL, because root DSL give us very easy way to name a particular node in the graph. Therefore, we can distribute the graph at much bigger chunks instead of some other platform have to distribute the node one by one, which turned out to be much less efficient. So this is one example of handling large computation. By actually, like a million node graph is by no means reaching our limitation. So we can routinely handle graph as large as hundreds of millions of nodes. That is not a problem at all. So really want to emphasize that the solution is generic and can scale up to the enterprise level. So the last example I probably wouldn't spend too much time on, but just quickly walk through the main conclusion is that oftentimes when you are building a machine learning model, or actually building any system, so to track your different configuration and experimentation is a tedious task. So sometimes you may have a machine learning model that you happen to train well and get a very good result, and a few days later, certain data input change, a certain configuration change, you can no longer regenerate that good result. This is often a very common problem in ML ops. So here we're going to illustrate how Julius can help solve this like a tedious ML ops problem by taking advantage the generic capability of reproduce and easily change the system. So in order to fully persist a distributed enterprise system, you have to do the following three things. So the entire runtime environment, including like hardware, like OS version, software library, all of this has to be reproduced, and then the input data has to be persist, and also entire code base, parameter, and configuration of the entire system has to be captured. So the first item, this is well solved by using Docker containers. That become a standard way of having a standard environment hardware OS. So that is well solved. However, the input data and the entire code base and configuration still remain hugely complex thing to capture, especially for when you have a system running on multiple machines and spanning a large number of components. So in this case, like when we take advantage of the graph computing platform in Julius, we make the entire process super easy. This is pretty much the same code as Mauro showed in the distributed machine learning use case. And we can see that once the user developer finished his development and get reasonable results, for example, if he is happy with this part of the results, what he can easily do is that he can create another cluster, a fresh environment that has nothing to do with the environment the developer used for coding. And from this fresh environment, he can easily send the same commands, send the same rules and items to this fresh cluster, and turn on the recording on the server side. So once the server side recording is complete, so you, here you let's see, show. Yeah, so once the server side, here we create a fresh cluster and we turn on the recording on the server side, then you send the same command to this new cluster, which you want to reproduce. And then we can take a serialized data structure of all the things that are happening on the server side that include your entire configuration environment, your all the things you need to recreate that distributed graph. Then you can persist this record in AWS or some other storage. Then later on, if you want to recreate this environment, you can just replay this record, and then you can see that in the end you exactly recreate the entire a distributed machine learning pipeline with identical results. So this is how easy we can help the developers to manage their machine learning experimentations. So whenever they have a good results, they want to persist, they just take a few lines of code to record it on an entirely brand new environment. And if you ever want to retrieve and recover that environment, you just replay it, and it becomes instantaneously available and to be identical copy of your previous configurations. So this is the last example I want to share. So now let's open it up for Q&A. I'm going to add my colleagues to the screen, and if you have any questions, please feel free to ask. So let's see if there's any questions coming through from Pigeonhole. So if there are no new questions, I'll probably just go through some of the old questions to make sure we have adequately answered them through the Pigeonhole. Yeah, so there is a question about how can we catch the best model. One of them using either for batch or streaming predictions. So we just showed that how easy it is to take a record and replay that record. It works for both batch and streaming mode. Yeah, there is a question about what is the advantage of using a graph-based approach compared to a conventional one for machine learning problem? Yeah, so this all goes back to the stellar advantage. So if you want scalability, transparency, explainability, lineage, low code, reproducibility, and adaptability, that's really you should look at a graph-based solution. The conventional programming language, you have to solve this problem on your own. So
I think below there are some questions with no answers.
Yes, there's a question about training in Python. Why did we train in Python and not in Julia? Of course, you can train in Julia. The Python example was to show the interfacing capabilities. And of course, Python is widely used for machine learning, so that's why we chose this language. In my case, it was not distributed, but as Mauro shown, you can also distribute a machine learning training process.
Yep, so certainly you can use Julia version as well. So there's a question about about pre-compilation overhead in graph computing for the whole pipeline because of Julia pre-compilation. So yeah, this is a good question. So it's true that we do have this pre-compilation overhead. So the first time you run the graph, calculation tend to be a bit slower. But the thing is, graph are geared towards like heavy computation. That a little overhead for pre-computation is not a big deal. If you look at end-to-end grand scheme of things. Yeah, there are a lot of questions we probably can't answer live online. We'll try to type in our answer in the Pigeonhole in the chat room. So I don't know if there's more questions coming through. Yeah, there's a new question. What do you see as your current biggest challenge as in using or developing this computational framework? Right, so that is actually a very good question. So I would say, maybe like Mauro or Melina can share your thoughts. I would say that graph computing is a very new concept. Not too many developers are familiar with it. So I would say probably require a bit learning and education to get used to the way of thinking. Because if you think in the graph construct in the graph manner, it's different from thinking in terms of traditional imperative function way of programming. So I would say that that changing in your thinking about computation is probably something we need to work more on to get the developer comfortable and see the benefits of graph computing.
Yeah, indeed, I agree. This is a difficulty that may arise, but you can deal with it by training, by seeing some examples. Especially this kind of tutorials are really helpful for doing this.
Yeah, there's a new question: how to deal with errors in certain node if they occur after data upload or new execution, maybe new parameter. Yeah, this is a great question. So we didn't show this part of the functionality, but we support the generic trigger. So you can define a generic trigger mechanism on your graph that can monitor any of these runtime exceptions or runtime conditions. So it can be data error or certain nodes running too slow or data arrive not in time. So once you have the trigger attached to your graph, whenever this condition happen, you can define your handler so that depending on how your handler is written, you can do different things. So for example, you can ignore the error, you can page a developer, or you can try to roll the previous value forward. All of these different strategies you can code in your trigger handler. So this is a very generic way of handling errors or any kind of runtime exceptions you may encounter during the graph computation. It tends to be very important for running like a large production system because you cannot possibly leave it to human intervention every time this condition occurs. So the next question is there any introductory published books for graph computing with Julia? I'm not aware of any, but yeah, maybe that is a good suggestion. Probably someone should write one. So it looks like there's more question coming in. Let's wait a few more minutes. There will be a presentation from our CEO, James Lee, in the main conference. So certainly you're welcome to join that presentation about the Julius technologies as well. Okay, so I think probably we can conclude this workshop. Let me just at the end share some of the links that will be useful for people to find relevant materials. Just one. Yeah, I'm going to share my my screen with a couple of last page. Oh, there's a new question. Okay, let's answer this new question. Regarding persistent, that is, thanks for the comment. Oh, great. Yeah, it's a comment, not a question. I appreciate your nice comment. So we're going to share a screen with a few links so that if you want to find the material afterwards, you can have the link in the video. Right, so here on the screen, we're showing the link to sign up for our developer environment, and also a few other resources that please feel free to browse. And also the second page is our blog pages and our email. If you want to reach out to us, ask questions, please do so using the email, or leave a comment in our LinkedIn pages. I think we can conclude this workshop. Thank you very much for joining, and look forward to hear from you.
Bye-bye. Thank you very much.
Bye.
Bye-bye.
Thanks for joining.